This video covers substitution instances, which are the concept that underlies the idea of a proof. And proofs are the main topic for the chapter we are beginning now. Earlier, we made a distinction between syntax and semantics. These were two separate ways of thinking about sentences. Syntax was the study of rules for manipulating symbols, sentences, without reference at all to what those symbols mean. One of the things I mentioned was that you can think of a digital computer as a syntactic machine. It is able to manipulate symbols, but it doesn't know what they mean. You can type search for celebrity name and net worth, and it will find those words, but it doesn't know what it means. Semantics, on the other hand, is the study of language that includes the meaning of the parts of language. The truth table method that we were studying in the last chapter was a semantic method for determining the validity of arguments. This is because the truth table method looks at whether the statements are true or false, and that's a part of their meaning. This gives us a notion of therefore, of entailment, of validity that is specific to semantics. And we symbolize that using the double turnstile down here. This is the semantic therefore. It says that this conclusion follows from these premises according to semantic methods of confirming validity, such as truth tables. We're also going to have a syntactic therefore, which is this single turnstile. This represents syntactic entailment. This will be a separate way of showing that arguments are valid. In sentential logic, the logical system we are currently developing, the semantic method was truth tables. We went over those in Chapter 7 of the current version of the text. The syntactic method will be derivation, or proof, and this is what we are going over in Chapter 8. As it turns out, the semantic and syntactic methods will be equivalent. Anything you can prove using truth tables, you can prove using derivations, and vice versa. Also, anything you can't prove using truth tables, you can't prove using derivations either, and vice versa. This is fortunate. This shows that we have set up our system properly. Okay, now just for a bit of review, show these two arguments are valid using truth tables. So on the right we've got one that starts with a disjunction. On the left we have one that starts with a disjunction. On the right we've got one that starts with a conditional. These are two separate ideas, so we're going to need separate truth tables for them. Go ahead and write these up just for practice. Pause the recording while you're doing that. You should have written up something that looks like this, right? So for each argument, any line that you can find where both premises are true also winds up being a line where you've got a true conclusion. So both arguments are valid. Now, think about these two statements here. So the first one is just the argument we were looking at before. P or Q, not P, therefore Q. If you knew that was valid, and you do now, you just showed it, do you really need a separate truth table to show the argument below? A and B or C, not C, therefore A and B. Look at them closely. Look at them together. You can see that each of these arguments lines up. The first premise is a statement whose main connective is a disjunction. The second premise is a statement whose main connective is a negation. And the conclusions can just be blopped together. So you can think of the first premise as a statement of the form A or B, where we're using our script letters here as metavariables. The second premise is the negation of the right side of the first premise, and the conclusion is the left side of the first premise. These two arguments are the same. And yet, if we were to draw up truth tables for them, they would be completely different. One of them would be much longer and a bigger pain in the neck than the other. At the very least, it should be clear that if you're just looking at two arguments that only differ because they use different sentence letters, but otherwise have the exact same form, you shouldn't have to do separate truth tables for these. So let's just go ahead and say that any argument that looks like this, A or B, not A, therefore B, is valid, where the script letters, because they're metavariables, can stand for any sentence in SL, no matter how long, right? So this is our argument scheme up top, and we're going to say that anything that comes from that is a substitution instance of that scheme, and it will also be valid. So for the left one, we just substituted A for A, B for B. For the center one, we substituted a longer sentence for A, X implies Y, and then Z for B. The next sentence after that becomes even more complicated, but they're all basically the same. They are all substitution instances of the same argument scheme. Your homework for the next section is just going to be about identifying which individual arguments are instances of more general argument schemes. And we're going to look at two argument schemes to begin with. The one that we've been discussing so far is disjunction elimination. It's pictured on the left. We also will be discussing conditional elimination, pictured on the right. Disjunction elimination is really just the process that you're familiar with of called the process of elimination, right? If you've got two options and you rule out one of them, then you know the other one must be true. Now, suppose we wanted to show something more complicated. Suppose we've got this argument, not L. Not L implies J or L, therefore J. We can actually use our ideas about substitution instances to show this, even though it is not a substitution instance in itself of one of our arguments. To show this, what we wind up doing is stringing our argument schemes together to show that you can move from the premises to the conclusion. And this is going to be the process that takes up the bulk of this last chapter. This is the process of derivation, or proof. So think about it this way. You can break up that longer argument into two smaller arguments. The first one has as its premises, not L implies J or L, not L, therefore J or L. You should recognize that as a substitution instance of conditional elimination. The second argument takes its first premise from the conclusion of the first argument and adds a new premise, not L, which actually we already knew, to get you the final conclusion, J. This, again, is a substitution instance of an argument scheme we've seen before, in this case, disjunction elimination. So we can string these two arguments together to get a proof that the larger argument above is also valid. When we do this, we'll be writing things up like this. For step 1, we write the two premises on numbered lines, and then off to the right, we write want conclusion, right? We just say that's the thing we're trying to find. In this case, it's J. We can build that up. For the next step is to write line 3. We write out the conclusion to the that we can draw from the first two premises. That was argument 1 on the previous slide. We justify this by saying that it comes from conditional elimination in the two previous lines. The final step is to write J on line 4 and say that that comes from disjunction elimination in lines 2 and 3. And this finishes our derivation because we now have the last line of the proof is the thing we want. Now you won't have to be doing these derivations yet. This is just to preview where we're going with the concept of substitution instances.